Hey, I'm Connor Smith with Warrior Sailing. Welcome to Battleborn Batteries Educational Series, the basics of lithium battery power systems for marine applications sailboats. My hope is that through this course, you'll be taking a very important first step to getting out there and staying out there. Let's talk about energy audits. As you can see, there are a lot of pros. It's important to have a good multimeter aboard them. I was really fortunate to grow up sailing since I was literally 3 weeks old. And I was also homeschooled on a sailboat. And I was literally designing and living off-grid power systems when I was 10 years old. I've gone on to become an ABYC electrical technician. I'm just so happy to be able to apply my sailing and electrical skill sets and help out Warrior Sailing. So Warrior Sailing is an organization to help ill and injured veterans recover and heal. We provide emotional, physical, and mental therapy through the medium of sailing. We have found that sailing is a great tool because it's mission-oriented and teamwork-focused. If we called it group therapy, nobody would show up, so we call it offshore sailing. Okay, let's get started. So what are the common types of batteries used on sailboats? So on my right are lead-acid batteries. These have been used for decades. There's different varieties. There are flooded lead-acid, just shown here. There's AGM. And there's also gel batteries, but they all have very similar charge and discharge characteristics. On my left is the newer technology, lithium iron phosphate. These batteries are made by Battleborn, and they all are built with a similar form factor to their lead-acid counterparts. Here are two 8D batteries, and over here is a new battery featuring wireless communication. What are some of the benefits and considerations when upgrading from lead-acid batteries to lithium iron phosphate on your sailboat? Well, one, lead-acid batteries like to be fully recharged after each discharge, and that's really challenging on a cruising boat. Often we are off the dock, away from shore power, and it's hard to fully recharge it, which is the cause of death for so many lead-acid batteries. Whereas lithium iron phosphate operates really happily in a partial state of charge. The other issue with lead-acid batteries is the recharge time. The current that a lead-acid battery can accept decreases as it finishes its charge. So the last 10 or 20% of the recharge takes longer and longer to complete, whereas lithium iron phosphate has a much higher acceptance rate all the way to the very end of charging. A pro to upgrading to lithium iron phosphate is usable capacity. So lead acid, you are restricted to about 50% of the battery. More than that, and the number of cycles that you're able to get out of the battery decreases dramatically. Whereas with lithium iron phosphate batteries, especially those from Battleborn, you're able to use the full capacity of the battery. Another pro in upgrading from lead-acid batteries to lithium iron phosphate is temperature-related degradation. So a leading AGM brand states in their manual that you can expect a 50% decrease in overall life expectancy of the battery for every 18-degree Fahrenheit rise in temperature above battery happy temperature, which is about room temperature. Whereas with Battleborn batteries, lithium iron phosphate, we see that at temperatures over 100 degrees Fahrenheit, we only see a 30% degradation in overall life expectancy. So finally, there's the weight consideration. Lead-acid batteries are much heavier than the newer lithium iron phosphate technology. This is about 160 pounds. It's quite hard to move in and out of the boat. This is about half the weight. So it depends where the batteries are mounted in a sailboat. If they're down low, the weight savings isn't really that much of a overall improvement, but it depends if the batteries are mounted in a poor location, too far forward, or in a location that's hard to access or might affect the sailing performance of the boat, then the weight savings can be useful. So as you can see, there are a lot of pros to upgrading from lead-acid batteries to Battle Born's lithium iron phosphate batteries. But there are some other important considerations when considering this upgrade. So can you and should you install lithium iron phosphate batteries in your sailboat? So there are a lot of considerations here. While Battle Born battery does make a battery that'll fit in your existing form factor aboard, there's many considerations, and you have to look at every single component in your own electrical system to see how the batteries would work within your vessel. For example, your charging sources. So your old lead-acid battery bank likely had a different charge profile than what is required with lithium iron phosphate. You have to be able to program it with the right values for this new battery technology. Also, lead-acid batteries required temperature-related voltage compensation. At cooler temperatures, require a higher charging voltage. But you have to ensure you can remove that functionality from your charging sources. Another large issue can be your electric anchor windlasses, electric deck winches, or bow thrusters and stern thrusters. These require huge inrush currents, and that can be challenging sometimes with lithium iron phosphate batteries that have a BMS that's designed to protect the battery. So it's possible in your situation you might need a separate windlass or bow thruster battery bank to power these large inductive loads. So another consideration is battery monitoring. In the past, with lead-acid batteries, you could roughly understand the state of charge of the battery based upon voltage. And that wasn't a perfect solution, but it could work because as the battery state of charge decreased, the voltage would also decrease. But it's a lot different with lithium iron phosphate technology. These hold a very constant voltage right to the last point of state of charge, and it drops off very rapidly. So you have to have an installed battery monitor to record the state of charge of your battery bank. Another very important consideration is the alternator charging from your engine. So most sailboats will have a diesel engine. This will have an alternator that's meant to recharge your house bank. So what's very important is to consider is how to integrate that charging source with your house bank safely, because an unexpected shutdown of your BMS could severely damage your alternator and your boat's electronics when the batteries protect themselves with the BMS. So you have to incorporate either a DC to DC charger to charge your house bank from your engine start battery, or have a very smart regulator driving your engine alternator that will safely charge your batteries. Another consideration is paralleling a house battery and a start battery. Some boats, including the one I'm on right here, has an emergency parallel switch that when engaged will connect the house battery to your engine start battery. So your vessel should have a dedicated engine start battery. And in the past, you could have a parallel function that would bring the two batteries together if your start battery were to die, but is not recommended with lithium iron phosphate. So you have to remove that parallel connection function with another means, such as a DC to DC charger to charge your start battery from your house battery. Finally, it's important to understand what a BMS shutdown is and how that can affect your vessel. So inside of all of Battle Born's batteries is a BMS, a battery management system, and it's looking and monitoring for proper voltage, current, and temperature. And if it goes outside of a certain bound or range, the battery BMS will take the battery offline to protect the battery, but it's going to leave the vessel suddenly without power. And that can affect bow thrusters, your instruments, autopilot, your entire electrical system. So it's very important to understand how that can affect your vessel You have to have a plan or contingency to operate in the situations until the power comes back online. But some great pros after personally living with lead acid batteries for so long is it reduces battery anxiety. I used to constantly monitor the battery state of charge because I was trying to always get the batteries to fully recharge each day. So I was trying to guess how sunny it was going to be that day, when should I run my generator. It was a constant thought, what state of charge my batteries were currently at. So it reduces that battery anxiety because these batteries are happy living in partial state of charge levels. Another pro is that lithium iron phosphate batteries are more efficient. A lead acid battery, you have to put more power into it than you took out of it to fully recharge it. Whereas a lithium iron phosphate battery is almost 99% efficient, which means requires a lot less energy to fully recharge it after you discharge it. So if you have solar, for instance, you're able to put more of that power into recharging the battery as opposed to generating heat in a lead acid battery. And lithium iron phosphate batteries accept a higher charge rate further in the state of charge, which means you can more quickly recharge them when you're running an engine or generator, which means faster recharge with less engine or generator runtime. You get to put more usable capacity in the same physical space, so you have more power at your disposal to use on your vessel. And finally, there's lifespan. These battle-borne batteries will last 3,000 to 5,000 cycles. You'll have more use of them with your time on the water. You've certainly heard the term lithium battery before, but let's be clear, we're talking about lithium iron phosphate. It is the safest lithium battery chemistry, and it is absolutely the best choice for your marine application. So which battle-borne battery is right for your boat? Well, it depends on what you currently have installed, because battle-borne battery makes a battery that'll fit your form factor to match whatever existing size battery you have. So if you have, for instance, group 31s, you can have a battery that'll fit in that same size, or 8D. All of these batteries have the same internal chemistry, lithium iron phosphate. If you are reconsidering redesigning your house battery bank storage and location, you should consider the Game Changer. So this is a proprietary designed battery from Battle-Borne, and it's designed to allow easy assembly of a large storage house battery bank. For instance, there's mounting feet with easy holes that can be bolted or drilled to locations. So a great design aspect is the terminal location. If you mount many of these batteries side by side, you can connect them in parallel very easily with bus bars or wires. Or you can similarly run them in series very easily, positive to negative with batteries alongside. If you have an 8D battery already installed, it should be easy to use your existing connections, but as you can see, it's a lot harder to make those same connections on this form factor. And most recently, there's the new batteries that will have communication technology. So this communication technology that allows you to monitor all aspects of your battery is going to allow safer integration in your boat or marine application, and also it meets the new ABYC standards. And ultimately, this feature will be available across all of Battle-Borne's battery models. A super common question we get is, can you start an engine from Battle-Borne batteries? The answer is, you shouldn't. You can sometimes in a pinch, but you have to have a large enough house bank to do that, but it is not recommended. It is best to use a lead acid battery to start the engines. In that role, a lead acid battery is really good to starting engines. It can provide a large inrush current and is very quickly recharged, and a quality lead acid battery will last many, many years happily starting engines. But when you're looking at a house bank, that is where battle-borne batteries thrive, because lead-acid batteries really struggle with longevity when they're not fully recharged. But a lithium iron phosphate battery works in that application very well. And while a lead-acid battery is great at starting an engine, it'll die very quickly in a house bank when not often recharged. So we recommend for house banks, you should consider lithium iron phosphate technology from Battle-Borne. So what is a BMS and how does it protect your power system aboard your vessel? It is a device that sits internal to each battery to keep the battery operating within its safety envelope. It's specifically designed to protect the battery and the user from operating in any unsafe conditions. The conditions it's monitoring are low voltage, high voltage, low temperature, high temperature, and high current discharge conditions. And if any one of these situations arises, it'll disconnect the battery to protect it and the system. So it's very important to understand when each of these parameters are met, so you can design your system to work within the safety envelope. So all of these parameters are written in the Battle-Borne battery manual, so you can set all of your charging sources and discharging sources to work safely within that envelope. And this is also good to design a safe system, and it obviously meets ABYC E13 standards. So it's also really important to note the BMS does not look at high charge current rates. That's left to the user to design a system that keep the charge rate under the recommended half C charge rate. So what are the common ways of recharging your batteries on a sailboat? The most popular options are with a AC to DC charger, and that can run off shore power if you're in a dock, if you're on a slip connected to mains on land, or if you're out traveling and you have a generator, you can power that same charger that converts AC to DC and recharges your batteries. Also is solar power, which collects the sunlight, transforms it to DC power through a MPPT charge controller. That's important to use as opposed to the cheaper PWM charge controller. So get a quality MPPT for use with solar. There's also charging from your engine on board your boat. Your engine's equipped with an alternator, and that can recharge your batteries one of two ways. Either it can recharge the start battery of the boat, and you can recharge your house bank through a DC to DC charger, which is a very simple option. But unfortunately, it can't utilize the benefits of lithium well because it can't direct all of that power available from the alternator to quickly recharge your house bank. So the other way is to directly connect your alternator to your lithium iron phosphate house bank. But you have to be very careful with that. There's lots of considerations to go into that, such as using a proper alternator regulator to make sure you charge the house bank safely. And of course, there are other options, although a little less frequently used, such as wind turbines or hydro turbines used while sailing, or sometimes even methanol fuel cells, although that can be very expensive. Using your boat's engine is a great way to recharge your Battle-Borne house batteries. But it has to be done very carefully, and there's a lot of considerations that go into this. The reason we talk about it so much is because using your alternator to recharge your house bank, it is a unique charge source that can be damaged if your battery encounters a BMS shutdown event, and it can also damage your boat's electrical system. The whole issue arises in that your alternator is spinning really quickly, putting huge amounts of power into your battery bank. And if all of a sudden there's a fault condition in your electrical system that requires your BMS to protect the battery and remove the batteries from that electrical system, your alternator has nowhere to put that power, and it often damages, catastrophically sometimes, your alternator. And in that process, it can severely then damage the electronics in your boat, which is something we never want to happen. So it's very, very important. We put lots of consideration into this, and this is done really correctly. So what do we do to charge correctly from the engine? Ideally, we would put all of the available power from the alternator on the engine straight into the house bank. Because lithium batteries, especially lithium iron phosphate, can take a very high charge level right to the very end of state of charge, right till it's done recharging. So you'd want to put as much power into the batteries as you can. So it is preferred to connect it in that manner to get the maximum amount of charge back in your house bank. But it's also the riskiest for your engine alternator. If you do go that route, it's very important to use quality regulation of your alternator. This is an external regulator. It tells your alternator exactly what to do and how to charge your battery bank. And this can communicate and accept data from all types of information sources on your boat, and it is the best chance at safely charging these house batteries. So if you do decide to connect your alternator directly to your house bank, the Wakespeed WS500 is the best tool to control your alternator and do it as safe as possible. The other way, though, is to use a DC to DC charger. This is very easy, it's very safe, but it doesn't transfer as much power into your house bank as quickly as the other options. So in this setup, you would have your alternator in your engine directly charge the start battery that it just started from, and then this DC to DC charger takes power from that start battery and charges it at the exact right voltage that the house bank calls for. And if there ever was a problem with your alternator or your regulator, it would all be contained on that side of the system, and it wouldn't get transferred to your house bank, which is running all of your critical electronics aboard your vessel. So what the heck is an amp hour, and why don't we use kilowatt hours, and how do you convert back and forth? So boats originally were equipped with an amp meter. It would measure how many amps were being used on the DC system. So it's easy to talk about how many amps of power an appliance was drawing. Therefore, we want to know how many amp hours our batteries held. So for instance, the 8D battery here from Battleborn Battery states in big letters 270 amp hours. But how do you use that number? So amp hours is literally the power of the appliance or the power available in a battery times a certain time. So this is in fact a total energy, because it's power times time. This is very similar to kilowatt hours, because this is power times time, also an energy. The only difference is this amp has an assumption of a voltage. In our boat, we have a 12-volt nominal battery bank. So we are assuming we're using 12 volts with that certain amperage we're recording. So if you want to convert amp hours to kilowatt hours, you just have to multiply the nominal voltage of the system. Now in a lithium-ion battery bank, specifically lithium iron phosphate, it's about 13 volts is probably a more accurate value than 12. So if you want to convert amp hours to kilowatt hours, you would multiply times, let's say, a nominal voltage of 13.0. So in this case, we have 270 amp hours times 13 volts equals 3,510 watt hours. And if you want to go to kilowatt hours, you divide by 1,000, and that total battery capacity is 3.5 kilowatt hours. Another common question is how to calculate power. In this case, power, we're going to call P, is equal to, and bear with me here, I times V. I stands for current, so I'm going to rewrite that here. Power, which is usually expressed in watts, equals the current, I, which is in amps, times V, which is usually in volts. So if you're trying to calculate the power, you'd multiply the current times the voltage, or vice versa. So if we're interested in how much current will run through a particular wire, for instance, we can divide everything by the volts. This cancels. So the watts divided by the volts is equal to the current in amps. So for instance, if we have a 1,000 watt microwave of interest, and let's say we run that through an inverter, and that's going to be drawing the power out of the batteries at, let's say, 13 volts. That's going to equal 76.9 amps of current out of the DC battery bank. So what is a battery monitor and why is it important for your boat? It's very important to be able to tell how much battery power you have remaining in your house battery. We've gotten away with it in the past with lead acid batteries because as the batteries discharge, the voltage slowly decreases over the state of charge. So you could get a rough idea of how much power or energy you had remaining in your battery bank by looking at your voltage. But even then, that method has issues, and it's important to have a battery monitor. It's one of the first upgrades you should do in your vessel's electrical system. But if you are considering switching to lithium iron phosphate, that becomes a should do to a must have, because lithium iron phosphate chemistry, it maintains a constant voltage almost all the way through its state of charge and then rapidly drops off. So the only way to know how much energy is remaining in your batteries is by measuring how much power went in and how much you have extracted. And so it's basically like a fuel gauge. It measures a state of charge of your batteries. What are your options to actually install a battery monitor? The first option is to use a shunt, and that installs in the negative lead to the house battery bank. That way all of the current that runs in and out of the battery is forced through this one device, and it can measure everything in and everything out. You can, such as the BMV 712, this will do that functionality. This talks directly with the shunt on your battery. Or there's a smart shunt, which will do that same procedure wirelessly. Both of those options can communicate with the Sailboat GX, which can send that, amongst a lot of other data, to a convenient touchscreen, such as the 7-inch touchscreen. But a newer option to measure the battery's state of charge is to use the new Battleborn battery with Dragonfly intelligence. And that is a new hardware that's installed inside the battery that monitors, amongst a lot of other things, the state of charge of each individual battery. And if you network that data together, you can have a precise measurement of each battery state of charge. So those are your options for battery monitoring. So now we're going to use our installed BMV712 running this system to do electrical energy audit aboard this vessel. So let's talk about energy audits. What is it and why should you perform one? So an energy audit is a way to identify the loads of all the things you have aboard your boat, like microwaves, coffee makers, lights, refrigeration. And it is really helpful because it allows you to properly design an electrical system for your boat. You have to understand how much you're using in order to understand how much energy you need to store and how much you have to generate to put back in your batteries each day. So there are two ways to do an energy audit, in my opinion. The first is to look at each appliance's power usage, and then we can assume a duration for that appliance. But the other method we'll go into in a sec, but both of these methods require a battery monitor to measure all of the power that's coming in or out of the battery and the state of charge. So here's the battery monitor in our boat. It's a BMV712 by Victron, and that just pushes its data to a Sailboat, which is beneath me mounted, to this touchscreen. So currently, the inverter is off, so I have no AC loads, which are the high voltage loads. My battery status, I'm at 100% state of charge. I'm currently drawing 22 watts, which is the total power, and that equates to 2.2 amps at the battery's voltage of 13.3 volts. So what's drawing 29 watts right now? I believe the lights are drawing some. So if I turn those off, we see it got a little darker in here. I'm down to about 15 watts. It's a little bit of a vampire draw. I think we have 11 watts now. That's the little bit of background lights on some of my instruments, drawing a little bit of power. But that's kind of the baseline right now. I'm drawing 15 watts. So I'm going to turn lights back on. So we see lights now. My total loads are at about 30 watts. So all the lights in the boat are drawing about 15 watts of power. So if I were to try to estimate over a 24-hour cycle how much that the lights will be drawing out of my batteries, I have to assume a duration. For instance, let's say I use the lights for 10 hours a day. So 15 watts times 10 hours is 150 watt hours, or 0.15 kilowatt hours. So I can go through each device now and see how much it draws. For instance, so my new baseline with the lights on is 29 watts. Let's see the water pump. So if I turn that on, it's going to draw a lot. You're going to hear it running right now. So I'm at about 85 watts, 100 watts, 120 watts. So that draws about 70 watts or so for the water pump. Other things like my deck lights, if I turn that on, it goes from 29 watts to 44 watts. And I can continue this here. Certainly my navigation instruments, these are going to draw a fair amount. So I went from the 29 watt base load, now I'm slowly warming up, passing 70 watts. So I see they're drawing about 50 watts right now. Turn those back off. How about some AC loads? So I'm going to go turn my inverter on, which is going to be busy converting the DC power into AC power to run kind of, I call convenience appliances, things we don't really need but we like microwaves and coffee makers and computer laptop chargers. So we're on now, we're inverting. And what's interesting, so I'm drawing 14 watts out of the outlets. Those are my loads. And so I only have, the inverter only powers my outlets aboard. So 14 watts accounts for things like again, little vampire loads like this temperature sensor, some vampire draw on a TV or a microwave, but that's my kind of new baseline. So let's go turn some other things on, see how much power it draws. So over here, I have a microwave. I've already put some bowls of water in it. So my baseline load right now, I have 15 watts of power being drawn on my outlets. I'm going to put this on for a minute. So looking at my loads, I've gone to, looks like it's selling at 1200 watts. It's a lot of power. So minus the 14 watts initial, I'm drawing 1200. So it's about 1190, 1200 watts. It's quite the load. A lot more, you can tell, than the lights. You know, that's a significant portion more. But the beauty is you only run the microwave for a couple minutes at a time. Coffee maker, the load, residual at 14 watts. I'm going to turn the coffee maker on. Now the coffee maker, I'm drawing 605 watts right now. So about 590 watts of load. But again, that's not all that, it's a large amount of instantaneous power, but it's not that cumulative amount of energy. It's actually quite small. If you figure that you only are drawing 600 watts for 5 or 10 minutes a day, that's only a portion, a tenth of an hour. It's a very small amount of total energy. So how do you calculate your total draw for the day? I now know the instantaneous load of each item. I kind of assume a time that's going to be drawn. So this coffee maker draws 600 watts or equivalently 0.6 kilowatts. If I only do it for a tenth of an hour, that's 0.06 kilowatt hours. And if I do that same procedure for each appliance, add up my expected time using each one throughout the day, I have an expected energy usage for my boat for that day. And I should do that kind of at anchor and then at sea, so I figure out how using the boat my energy demands might be different. So the other option, which I like a little more, is to let the monitor do the work for me. So this is measuring the total amount of power I've drawn out of my batteries. So if I have the battery monitor installed, if I'm at the dock trying to calculate my power usage, I can just live my life with the battery chargers off, and this monitor is going to measure the cumulative effect of me using all of my appliances how I actually will use them. So this will actually record my day-to-day life power usage aboard the boat. And once I know the loads while at the dock living aboard, which would be very similar to if you're at anchor, I'd want to do the same procedure using the boat, because underway I'll have loads like autopilot, radar, navigation lights, other things I'm not typically using at anchor. So it's kind of a different profile of energy usage. So once I have those two values, my actual power usage over a 24-hour day, now I can go in and design a proper power system with adequate energy storage and generation to recharge the batteries. So we've done the math now. We know that you calculated your total energy used over a 24-hour period. Likely, the amount of power that you use underway sailing will be more at anchor than your at anchor loads. So if, for instance, you did this math and you used 2,000 watt hours at anchor or underway, you use 2,500 watt hours. Let's use the larger number because you want to make sure you have enough power for worst case scenario. So we used watt hours. You could use amp hours. They're slightly interchangeable because we have a 12-volt system. But given batteries are often rated in amp hours, it's best to go back to amp hours. So let's do that. So 2,500 watt hours, you divide by nominal voltage. Sometimes you can assume 12. With lithium batteries, it's more like 13. let's be conservative and say 12.9 volts. That means your energy of 2,500 watt hours at 12.9 volts is approximately 193 amp hours. But that is you don't want to have, all your eggs in one basket and only have enough power for that. You want to allow a little bit of room for expansion on your system. You're always going to use more power in the future. Likely you won't be taking loads off your system. So you want to leave a little room to grow. Plus it's better for longevity of the battery to use the middle state of charge. Don't push it all the way full and drain all the way down. So let's multiply that needs times an extra 30%. So that comes out to be 250 amp hours of energy storage you should have in your house battery. So when you look at the battery options, you can either look for one battery that's big enough for that, but I'd recommend at least 2 batteries in parallel to make up that capacity that you need. It's important to note that when you convert DC to AC, there are always losses associated with that conversion of electricity. So a 1,000 watt microwave of AC power will draw more than that out of your batteries, such as 1,100 watts out of your batteries. So these calculations, the second method I mentioned, using the actual power that's pulled out of the batteries as recorded from the battery monitor, will capture those inefficiencies. So that's a good way of doing it. So that was a view of battery bank sizing, but that's very simplified. Obviously, every situation is going to differ. You may have lots of solar. If you are a catamaran, you probably will have lots of solar power. Or maybe you have a twin engine vessel and you have a lot of alternator power. Or maybe you're generator heavy. It's going to depend on your situation exactly how big your batteries want to be. Maybe you want to go out at anchor and sit quietly with no solar for 3 days. Obviously, you have to change those numbers on battery bank sizing. This is kind of the bare minimum. You need to apply it to your own needs, how you primarily want to recharge the batteries, and then figure out your exact bank size. So now that you've determined your battery bank size, you have to determine how you're actually going to install it. Are you going to do it in a DIY approach, or are you going to hire a professional? It's definitely not a decision to be taken lightly, because house batteries, as with all batteries aboard the boat, are no joke. They hold a ton of power. That energy can be released very quickly in high amperage current that makes a lot of heat. So if you do it wrong, there are serious consequences. So it's very, very important to install these batteries correctly with fine attention to detail, such as location and securing them with proper cables and fuses. So safety truly is paramount. You need to stay safe. And they really should be installed to ABYC standards. It's a great set of guidelines to help install batteries safely. So it's a little challenging to see how the components that we've talked about through these videos, how they're installed and interact with each other. Obviously they're here, they're just spread out through the boat. So when we head to the shop, we can see how all the components interact with each other in a nice, easy to view layout. So when you are designing your own power system, you have to determine both the capacity of storage batteries you need and the voltage your system will run at. And that configuration will dictate how the batteries are being connected. So let's look at the 2 ways to wire a battery bank, either in series or parallel. And depending on your situation, you might have to use one or the other or combination of the 2 methods. So this is a mock wiring setup powering an inverter. This system needs 12 volts. So let's first start off talking about a parallel configuration. So to power this system, you would connect these batteries positive to positive and negative to negative. We've maintained the voltage of the system, 12 volts. We now have over 500 amp hours of power available. And the way I would connect this to a boat or an RV, I would connect the terminals here and here, and that evenly distributes the load across both of these batteries. So here is a graphic showing a parallel configuration. So now let's talk about series. So we use series connections if we want to increase the voltage of the system. For instance, if we have a 24 volt, 36 volt, or 48 volt battery system, we need series connections. And you would connect them with a jumper between the positive and negative terminals here and here. Now, this system is 24 volts, and we would connect the boat or RV system leads here and here. And this is 24 volts at 270 amp hours. Now let's look at this graphic, which shows a series configuration. Another configuration is series parallel, where some batteries are connected in series, some are parallel. For instance, if we had two more 8D batteries and we wanted 24 volt system, you would connect these two in series, these two in series, and in the end, these two would be connected in parallel. And this allows you to build a system with as much capacity as you require and whatever voltage you need. So let's take a look at a graphic. We have a series parallel configuration. So let's talk about cable size. How do you figure out what size of cable you need to power your off-grid system? All of these wires you see here have the same voltage rating. As we see here, 600 volts, 600 volts. So they can all handle whatever voltage you need, no problem. But what dictates how thick the wire needs to be is the amperage and the distance of your circuit. So how do we know how much amperage will flow through our circuit? Well, it starts with trying to figure out what you're trying to power. For instance, on this setup, we have a 3,000 watt inverter we're trying to power from these batteries. So amps times volts is watts. So if we have 3,000 watts, that's the total power, at 12 volts, that equals 230 amps of current. In this case, we have a relatively short run to the batteries. It's maybe 6 feet long, total length from batteries to loads. So we would go to a table to look up the amperage and length of the circuit to figure out the given wire size we need. So there's one other complicating factor, and that's voltage drop. Despite our best efforts of having really large, thick gauge 2-watt cable, we will still have a little less voltage at this end than when we started. So what's the allowable amount of voltage drop? Well, ABYC, the American Boat and Yacht Council, gives guidance on that. And a circuit can either be designed for 10% voltage drop or 3% voltage drop. And that only difference is how thick the cable has to be. So on non-critical systems, such as inverters or lights, you can design your system with up to 10% voltage drop. For critical systems, such as bilge pumps and navigation equipment, you have to design the circuit with 3% voltage drop, which will make the wire size a little bit thicker. I like to keep it simple and use an app. It helps to factor in all these different complications and gives us an easy way to calculate the wire size we need for our system. So the app I like to use is Blue Sea Systems Circuit Wizard. There's a function here to calculate wire size. You can put in all of the variables you need, such as volts. In this case, it's a 12-volt system. The load current, we already calculated to be 240 amps. The length of the conductor, and that's the full circuit length from battery to battery, about 8 feet. Allowable voltage drop is 10% because this is just power and inverter. So the insulation temperature rating relates to the wire, and a good quality wire will have a 105 degrees centigrade temperature rating. It'll be printed on the side of the wire. So we input that here. If it's installed in an engine room, in this case it's not. There are wires in a bundle, we say 2 to 3 wires. The average duration of the load may be about 10 minutes, and it is terminated on a fuse. So we hit calculate. In this case, for this off-grid setup, we need 3/0 cable size. So when upgrading your sailboat's power system from lead acid to lithium, let's look at what some of the major components you would need. You need an inverter charger that is able to charge the batteries and convert that power to usable AC power. You need a solar input charge controller that brings your solar power in. In this case, it's an MPPT charge controller. Probably you'll have a DC to DC charger, and this is able to charge that bank from other sources, such as a start battery or other places. You'll also need a battery monitor. Typically, this is done with a shunt style monitor. It goes in the negative cable to the battery, and it monitors all the current in and out of the battery bank. So you probably already have the majority of these components installed somewhere in your system. But you have to go through each component and make sure it's compatible with Battle Born's batteries. So my recommendation is just call Battle Born's technical specialists, and they can check if your existing components will work with their batteries. So beyond the major components, you also have some small components to consider, such as a Class T fuse. This is recommended by ABYC to be installed immediately next to your batteries within 7 inches. And the Class T fuse will be able to protect the major wiring distribution from a direct short. Since these new batteries have so much power in them, it's even more essential than ever to have proper fuses in place. So it's also very important to have a main battery disconnect switch. So this would be just downstream of your Class T fuse. And the purpose is to shut off the entire battery bank if there ever was a problem. It has to be rated for the maximum amperage of the circuit. So it has to be a very large, powerful switch. And it goes, like I said, in the main conductor, probably near the battery bank or close to the fuse. Separate from the main battery bank disconnect, there should be a service disconnect for the inverter charger. And that switch also be very powerful because it has to disconnect the power leading to this large charger / inverter. It would be connected in the positive wire here. ABYC now states that the batteries must give an audible or visual alarm before the BMS shuts the battery down. So the new batteries from Battle Born, the Intelligent series, have wireless battery monitoring that monitors all aspects of the batteries, including state of charge. So a new system using this technology wouldn't require a separate shunt to monitor the state of charge of the batteries. When upgrading your house battery bank to lithium batteries, likely there'll be a bigger stress on the other electrical components of your system. You'll be asking to put more current through them to charge the batteries quicker and to pull power out of them faster than you were with your lead acid batteries. It's really important when you make this switch to give a good, thorough analysis and inspection of your electrical system and make sure you have fuses in the right places. So for instance, there should be a Class T fuse right off the main power conductor on your positive side. ABYC says it should be within 7 inches of the batteries. After the fuse, you go through a switch to a distribution block. And the beauty of this Lynx distributor is that not only is it distributing power across multiple big and small circuits, but it also allows you to put different size fuses for each of the different loads you are powering. So the beauty is I can have a large fuse, 300 amp fuse for the inverter charger, but I can put a 30 amp fuse for the small circuits that run to either power loads or to charge from a source such as your solar. So the idea is would be a branch circuit. You have a large fuse that covers the risk of short from these large conductors, and then on these smaller conductors you have a smaller fuse, because the same fuse that protects this large 2-watt cable won't protect this 8-gauge wire from a short. So you have to put a smaller fuse when you go from a big wire to a small wire. Then as you continue along, you transmit power to another distribution. You go from 8-gauge to say 10 or 14 gauge. The new smaller wire also has to have another fuse or breaker to protect it from a short. So in a proper power system, you'll have a fuse or breaker every time the wire goes from larger to smaller size. So what is a case ground, and why is that important on a multi-plus inverter charger? First, where does it go? So the case ground connects to this lug right here on the frame. So the idea is you have a large ground wire that goes from the case to your grounding bus, which is ultimately connected to the boat's neutral or negative battery post. So if there ever was an internal short or malfunction and this large wire were to touch the case of this inverter charger, it would electrify this case. But if you have the ground properly installed, it'll send that power safely back to the battery bank, and in doing that, will trip the fuse either here or within, in this case, the Lynx distributor, shutting off power and making that component safe. So while your ground, your inverter will still work without having the ground installed, it's very important to go ahead and install that ground. And it needs to be sized appropriately. This small green wire is for demonstration purposes, but the final wire should be as thick or 1 gauge smaller than the main conductors that feed the inverter charger. The Multi-Plus pairs very well with Battle Born's lithium batteries. But you do have to program the Multi-Plus to get all the benefits out of your lithium batteries and for the two systems to work well. So this is how you program your Multi-Plus inverter. So first, take off the bottom cover. There's 2 screws on each side, and this cover is removed. You want to disconnect any Ethernet cords that may be connected. You just want to talk to the Multi-Plus by itself. So I'm going to have a separate Ethernet cord, and that plugs into either of the VE bus Ethernet ports. So I connected it to one right there. Then, to convert it to talk with a computer, we use the VE bus to USB. This is the Mark III USB. So that connects. Then here, we simply connect to a USB port on a computer. And we're going to open Victron Connect to be able to talk with the Multi-Plus and program all of the proper settings so that these batteries get charged perfectly. So now we're going to head to the boat and we'll show you the actual programming steps. So welcome aboard Acadia. So we are going to continue where we left off. Just a moment ago, I showed you how to connect to the Victron Multi-Plus. I'm connected now. It is beneath my seat, and the Ethernet connects into the VE direct port. I have the MK3 to USB connected to the laptop. So now we're ready to program the Victron Multi+ 2. So I open up Victron Connect. We're now on the home page for Victron Connect, and I see 3 different pieces of hardware populating. We're interested in the Multi+ 2, so I'm going to select this hardware. It's connecting to the Multi+. Okay, we are on the home page for the Multi+ 2. So we see it's currently on. We have AC power coming in. It's recognizing the batteries. They are in a float state of charge right now. So we're going to go ahead and begin adjusting the settings. So you go to the gear icon. You have to enable settings. So now it's prompting us for a password. It's best to contact your Victron dealer to get the password to go in for these settings. In this case, Battleborn provided us the password to use now. So we're going to enter that and begin adjusting the parameters. So as you can see, there are a lot of settings in this menu. We're only going to adjust a couple of them to get the Multi+ to work well with these Battleborn batteries. But your setup might vary. So when in doubt, always contact your dealer for technical support. Keep in mind, if you do buy your Victron hardware from Battleborn, this will all come pre-programmed for you. So we go into the first tab under General, System Frequency. We're in North America. The frequency of mains power is 60 Hertz. We have a current limit currently enabled, which is 7 amps, and that just protects us from overloading the generator. But I have it selected that I can overrule that on the remote, so I can adjust that if I'm not running other things and working the generator hard. The dynamic current limit is another setting when you have a small amount of generator output power available. If you had some other hardware, such as an external current sensor or a second battery monitor connected to the Victron, you would toggle these on here. So going under the Grid tab, we currently have it toggled on to accept a wide input frequency range. It's not that necessary because the grid power is quite stable, but it doesn't hurt to have that on. The UPS function is something you want to be careful because it actually stresses the inverter charger. UPS means uninterrupted power supply. And if you have critical electronics, you'll want to turn that on, but if you don't need it, it's best not to toggle that on. Then we have certain disconnect and reconnect voltages. So if the grid voltage goes too low, below 90 volts, the input will cut off and it'll reconnect at 100 volts. And then same thing if the grid power goes too high, it'll disconnect at 140 volts and reconnect at 135 volts. Next, under the Inverter tab, so we are outputting 120 volts. The ground relay you want on. This is a setting to connect the output ground of your AC power to the input ground, and you do that when you're on shore power. The DC input low voltage shutdown. This should be set at 11.5 volts. This is when the charge gets to that point, the inverter will stop drawing power. The input low voltage restart, when the voltage goes above a certain point, 12.5 volts, the inverter will reconnect. And we have a DC input low voltage alarm. So if we get down to 12 volts, an alarm will go off to indicate the voltage is getting low. We have a low state of charge shutdown option. This is disabled currently. And here, this option, AES, is the automatic energy savings option. That is a feature that can save power by turning off the output of the inverter when you go below a certain load. I don't like that setting, so I leave that off because I have many loads that are quite small that I like to run constantly. The power assist feature is a feature where you can draw power from the batteries to assist in starting large appliances. when you don't want to stress the generator too much. So you use a little bit of power from the batteries to help get those hard loads underway and everything running properly. Under the charger tab, we have the charger enabled, so that way when we have shore power, we are putting power back in the batteries. The charge current is at 120 amps because that's the capability of the Multi+2. The absorption voltage needs to be between 14.4 and 14.6 volts for Battleborn's batteries. Currently we're set to 14.4. The float voltage needs to be set between 13.4 and 13.8. So we're currently set at 13.4. The repeated absorption interval is the charger, when it's plugged in to shore power for long periods, it'll return and top off the batteries. And so every 7 days, it'll increase the voltage and recharge the batteries, which is good, so that way all of the cells stay balanced. So the absorption time, that is recommended to be set between 0.2 and 0.5 hours for every 100 amp hours of battery capacity. In this case, I have 500 amp hours of capacity, so I'm going to set this to about 2 hours. The low temperature cutoff, that stops the charger from charging the batteries below a certain point, but since the batteries have a BMS, I'm going to leave that option disabled for now. A very important selection is the lithium batteries tab. Make sure that is on. It's going to stop any voltage change based upon temperature, which you do not want for lithium batteries. So you see the charge curve is fixed as a result of that. The next two options are disabled because we have the lithium battery selection selected. If you have problems with your AC input, you can adjust the weak AC input selection. And then the final safety setting, stop after excessive bulk charging. If you keep throwing lots of power at the batteries and it's not finishing the charge, this will recognize that and stop charging. So finally, under AC input control, I don't have any of these selections selected. For my instance, I don't need it, but it can depend. If you have certain power inlet requirements, you can adjust these settings. So now all of these settings have been adjusted. We're going to push these settings to the inverter. We do that by hitting reset now, and it's going to cut off the output power as it resets itself. It's going to disconnect and reconnect now. Sounds like it's back reconnected. We're going to open Victron Connect again. So great, I can hear the charger charging again. Multi-Plus is back on. I can select it. We're back in bulk charge because it's restarted itself. It needs to try and bring the batteries up. They happen to be full, but it's going to try and charge them again anyway. But that's it. Those are the settings you need to adjust for your Battleborn batteries. But once again, this programming is pretty advanced. So if you have any questions or need help during this process, you can contact Battleborn's technical specialist for assistance. So it's really important to have a good multimeter aboard the boat. This will help so much in troubleshooting the systems you have, finding faults, figuring out if equipment is defective, but also helps in the installation to ensure the connections are clean and everything is connected properly. So there's three main functionalities of a multimeter that you should be aware of. So be able to measure AC and DC voltage, AC and DC amperage, as well as continuity. So we'll start with voltage. So I'm on volts right now. This meter can measure both AC volts and DC volts. AC volts is like your shore power coming in from land or from your output of your inverter. It's demarked by the little sinusoid. So since I'm measuring DC volts right now, I change the mode to DC volts. I'm ready to use my prongs to measure voltage. So I can go on the terminals of this battery, measure, I have 13.1718 volts here. I can measure the other battery. Same, 13.17, 13.18. So that's the voltage. Now, the other very important parameter is the amperage. That is how fast the electrons are moving through the circuit. So in the amperage mode, I again select DC amperage. I have to re-zero out the meter before I start using it. So now we're zeroed out. So I'm ready to clamp this over a wire. In this case, I'm going to connect the lead to the battery, but this can be your alternator output. It can be your solar input. It can be really any specific thing you're trying to target. And if you have an issue such as a bad solar panel or something, you can clamp this around all the different solar inputs to see which one is being troublesome. So for now we're on amperage. I'm going to connect it here. So I can grab the positive lead, the amp clamp. We see I'm drawing 9.2 amps out of here, and we can check that everything's working because this is a circuit. Whatever's coming out of the positive has to be returning on the negative. So we can connect it around the negative, and we see we're reading the same power, 9.5 amps. What comes out must come back in. So this is great. If a battery were to be giving trouble, or if there was a fuse blown on a particular device, you could check to see if that device was performing by clamping around that particular lead. So finally, there's continuity. And that's the ability to have a complete circuit. So this tests to see if a complete circuit exists. And I touch them together, the meter beeps. So for instance, this metal is obviously conductive from A to B. But if you're having trouble with an appliance, you can see if the path to that route is conducting power. So this is a positive bus bar down along the side of this battery. So I can use this to test continuity. And if I am trying to show or trying to record that there's continuity between the positive here and the positive bus bar, I can connect the two leads. I can see that there's continuity. So it's a great troubleshooting tool to test that every part of the circuit is connected and working correctly. So as you can see, the multimeter is a very useful tool. It's something that every boat owner should have and know how to use. So when it comes to safety on a boat, there's two main concerns. DC batteries, they contain a lot of stored power, but it's at a low voltage. So that means when there's low voltage, there's less potential to jump across and shock you. For instance, at 12 volts, I can put my hand across these terminals and there's no electrocution. So it's very safe electrocution standpoint, but that's different than AC power. So this is shore power, essentially. This is 120 volts. This can actually electrocute me. If I do it really wrong, can kill me. So the big dangers from AC power, which is all through the boat, is electrocution. The big danger from DC power is shorts. So while I can put my hand across these terminals and not get shocked, if there would be a piece of metal to fall across these terminals and short out, that would cause an intense amount of heat that would melt something or catch something on fire. These batteries contain enough power to literally liquefy tools that might fall across it. So I need to get some covers to cover these terminals so that way any wrenches or tools that might fall in doesn't have the chance to short these terminals out. And I also have to be very careful of shorts in the wiring. Because this is low voltage, there has to be very high current moving to power everything aboard the boat. So that's why these cables are so fat. So while it's good to transmit power, it's dangerous because if these were to ever cross each other, for instance, if they were to, they're moving in the boat, you're sailing, they're chafing against each other, and conductor versus conductor touch, that's called a short because you're creating a shorter path for the power to circulate. If that were to happen, this would cause an immense amount of heat to build up in these wires and batteries, potentially causing catastrophic damage. So you have to be very careful where your terminals are. Nothing comes into contact with them. They should be covered. I'm going to be doing that. And these wires have to be protected, free from danger and chafe, and they have to be immediately close to a fuse. So the whole job of the fuse is to protect against a short. And if these two wires were to cross, the job of the fuse is to pop and separate that circuit to stop the excess current and heat from building up. So in this case, we have a Class T fuse. This is what is required by ABYC to be safe. This has the ability to interrupt 20,000 amps, which is the rating that's required for a lithium battery bank aboard a boat. So be very careful against chafe and shorts that would cause lots of heat around batteries. And when working around AC, make sure it's de-energized so you don't get electrocuted. And that's how you stay safe around electricity on boats. So here are a few electrical system maintenance tips for your sailboat. So we're looking here at the house bank. These are the house bank here, these two battle-borne lithium iron phosphate batteries. Thankfully, the only maintenance here is just ensuring that the terminals are tight and clean. And this is important because there is so much current that travels in and out of these batteries. If there's any dirt or corrosion in these terminals, they will get hot. You could potentially melt the insulation off the wires, or you could damage the battery. So we make sure regularly that they are clean and tight. When we do that, we use an insulated wrench here, so that way the rubber handle protects us from shorting across these two terminals. And I need a second wrench, so I should have had another one of these, but in a pinch, I can make up a little safety wrench by taking the proper wrench and coating it in a heavy tape such that it cannot conduct across the terminals. So with these, I can check all my connections. Ensuring, yep, nice and tight. That's just the way we want them. If there was dirt or needed to be cleaned, or if they get corroded, I can take the connection apart, take a wire brush or sandpaper, clean both sides really well, make all the corrosion is off, and I can put a little layer of dielectric grease between the connections and make them back up again and make sure they're nice and tight. So another maintenance item is always checking the right size fuse are installed. So the equipment changes with time. You reinstall or you change or modify. It's always important to be thinking about what fuses are where and how they're protecting your system. So over in this corner, we have a Class T fuse, and that protects all this large wiring as it distributes through the different buses and around the boat. If anything downstream of this fuse were to contact and short, that fuse would protect it. It's always important to think, is the right size fuse in the right place, and has anything changed since I last did an audit of my electrical system? And finally, so speaking electrical system, the other battery banks, this is a house bank. Beneath me over here is a starting bank. That's a lead acid water-filled battery used to start the main engine. That requires maintenance beyond checking the terminals. You have to add distilled water regularly, about once a month or so, to keep it filled up. Otherwise, you risk damaging that battery. So those are a few tips to keep your electrical system shipshape. So you're thinking of upgrading from lead acid to lithium iron phosphate, but you're wondering how long will lithium iron phosphate batteries last? Well, Battleborn states that after 3,000 to 5,000 cycles, around 80% of the usable capacity will remain. But here are tips to help you get the longest life and best performance out of those batteries. The first thing, you don't want to overcharge your batteries. Once you've recharged the battery, make sure the charger is backing off on its voltage and coming down to the float voltage of around 13.4 volts. So you can charge a battle-borne battery up to half C charge rate, but to maximize longevity, you can decrease that charge rate whenever possible, and that'll increase the lifespan of the battery. Also, whenever possible, keep the batteries cool. It's a lot easier because there's a lot less internal heat created in a lithium iron phosphate battery, but they love to be stored and used around room temperature or a little bit less. So whenever possible, keep them cool and at a comfortable temperature. So it's also very important to install the battery bank correctly. You have many batteries all wired together working as a house bank. You want to make sure each one is doing its equal share of the work. And so you do that by having the same distance of wires connecting them. All the connections are tight, and that will ensure all the batteries are used equally. And finally, it's really important to periodically charge at 14.5 volts. That allows all of these cells inside each battery to self-balance. And so you want to make sure if you're plugged into shore power for long periods of time that the charger will periodically return to a higher charge voltage to allow all of the cells to internally balance themselves. So these are a few useful tips to get the most out of your battle-borne batteries. So you have lithium iron phosphate batteries as your house bank, and you're considering solar to recharge it. It's a very natural choice because hopefully you're traveling in a place that has lots of sun. You want to use that energy to put back in your batteries to use for useful things like running your appliances. But how do you do that? What are your options? Well, you can get a flexible solar panel or a rigid solar panel. Flexible solar panels are generally more expensive, but allows you some nice options to either mount them on the deck in some places, and you can even walk on them depending on the solar panel brand. You can also mount them on curved surfaces like biminis and different dodgers, which can be nice for a nice streamlined look while maximizing your solar input. And there's also hard panels, which can be mounted in a frame, either also on top of your bimini or on a frame over the back deck, as some people choose to do. My personal boat, I used to have 600 watts of solar on an arch on the back deck, and that was really useful in covering most of my day-to-day electrical needs. And another great benefit, if I ever left the boat, I knew the freezer and the fridge would have enough power to remain on, and I could leave comfortably knowing if all the power in the dock goes out or if the boat's at anchor, I don't have to worry about my food going while I'm off the boat. Finding mounting locations for solar on a boat is very hard because there's always things in the way like rigging and antennas and lines, and you're always having a balance between the beautiful solar input and maneuvering around the panels. So you have to have some balance, and it changes from every boat on usage and design of that boat. So get creative and see what works best on your vessel. So what are the ABYC E13 standards for lithium-ion batteries? Well, the ABYC is the American Boat and Yacht Council. It's a member organization that sets voluntary safety standards for recreational vessels. These are a voluntary set of standards, but most insurance companies look to their guidance when approving policies, so they're very important to follow. And they also are designed to keep boats and vessel operators safe, so they're a very good set of standards to follow. Also note that these standards are also the minimum at which you can design a system. It's never a bad idea to exceed them and produce a system that is safer than what's described or required by ABYC standards. So the standards cover all lithium batteries that are installed on a boat. And they state that 1, you must install the battery to manufacturer instructions. The battery must have SAE, IEC, or UL testing certifications, which this rules out most Chinese or knockoff batteries. The batteries must be restrained very securely with no or little to no movement. These batteries must use a battery management system to protect the batteries and keep them working within their safety envelope. It requires warning of an impending shutdown condition through either a visual or audible alarm. It also requires information from the manufacturer about the usage of the battery, the proper installation of the battery, and the design parameters of the BMS. So this point is very critical because you have to know how the BMS is going to react. So if you know the parameters it's going to cut off at, you can design the rest of your system to work within that envelope to prevent any unwanted BMS shutdowns. And finally, the standards recommend alternative power sources for critical systems aboard the vessel. So given these new set of standards by ABYC for lithium-ion batteries, Battleborn Battery has come out with a new series of batteries featuring Dragonfly intelligence. And these new series of batteries internally record and wirelessly transmit all the operating parameters of this battery. So this is able to communicate with external devices that can set off audible and visual alarms to alert the operators of the boat of an impending BMS shutdown. For example, this alarm here. So that audible alarm that's able to be triggered via the communication from the battery goes a long way to making a better performing and safer battery bank. And of course, it matches and exceeds all of the ABYC standards. Thank you for joining us for this educational series. I really hope you enjoyed it. If you have any more questions, reach out to the team at Battleborn Batteries. In the meantime, I hope you consider supporting Warrior Sailing.